Howdy, welcome today to another recording on algebraic methods. So we've covered the proof aspect of algebraic methods, and now we're going to have a look at a really important application of essentially what was GCSE work, manipulating algebraic fractions. So at GCSE you may have been asked to add or subtract algebraic fractions to get them into a single one. Here we look at the reverse process where we take a factorised algebraic fraction and talk about how we can split it back into single fractions, which are called partial fractions. And this is going to have wide-ranging applications, particularly for integration, actually, which we'll see much later this year. So before we begin, I've got some warm-up questions for you to attempt. Here they are, questions 1, 2, 3, and 4. So I would suggest to pause the video here, try these on your own, and then when you're ready to see the solutions, press play, and hopefully the solutions you see will match your own. So assuming you've paused the video and had a go at these on your own, let's now have a look at the solution to worked example 1a and b. So for warm-up solution 1a, we're asked to simplify into a single fraction these two fractions, 4 over 2p plus 1 plus 3 all over p minus 1. Now, the way your teacher taught you this or the way you happen to do it now may be different to my own. My tendency here, my preference, is to do what I call the butterfly method, which is not exactly a technical term. To get a single common denominator, we can cross multiply and then just multiply the denominators by each other. So this numerator becomes 4 lots of p minus 1. This denominator now becomes 2p plus 1 brackets p minus 1, and the other with cross multiplication becomes 3 lots of 2p plus 1. Again, now all under the same denominator, which is 2p plus 1 multiplied by p minus 1. Because this is all now both the same denominator, I can combine these two fractions into a single one because the denominators match. So the common denominator now we have, which is 2p plus 1 brackets p minus 1. 4 lots of p minus 1 obviously becomes 4p minus 4, and over here 3 times 2p becomes 6p, 3 times 1 of course is 3, and so we can simplify this one more time to arrive at our final fully simplified solution. 4p plus 6p on the numerator becomes 10p, and minus 4 plus 3 overall is minus 1, and all that is over the denominators factorised into 2p plus 1 brackets p minus 1. And so that's the first one complete. That's 1a done. 1b is similar, even though we have slightly more awkward denominators. I've put these deliberately because sometimes, yeah, you may have a fairly awkward fraction to simplify. But because we're just adding or subtracting, again, we can use the cross smiley face method, or whichever method you're using, just check it is consistent with my solution. So, doing that, we're going to have two fractions, and they're going to have common denominators. So multiplying both denominators together, 5 times 3 gives 15, and multiplying the brackets, I'll leave them factorised. That's going to give me x plus 1, x minus 4, and the same denominator over here, 15, x plus 1, x minus 4. And again, it was one fraction minus another, so let's not forget about a very important detail. Stick the minus sign in there. This numerator, 3x multiplied by 3 gives 9x, then multiply by x minus 4. Over here, we're going to take 2 times 5, which of course is 10, and the brackets x plus 1. Because both these fractions now have a common denominator which is the same, I can combine these two fractions into just one. And what we can do is expand and simplify the tops. So the denominator, going to leave factorised as 15x plus 1, x minus 4, and this numerator will become 9x squared minus 36x. Over here, minus 10 times x, of course, is minus 10x, and minus 10 times 1 just gives minus 10. And final step, we can just simplify all of these terms on the numerator, giving us 9x squared minus 36x minus another 10x is minus 46x, and minus 10 just stays as minus 10, and all of that's over 15 lots of x plus 1 brackets x minus 4. So that's warm-up question 1 complete, both parts A and part B. Let's have a look now at warm-up question 2. Warm-up question 2, we have to express this as a single fraction. So the key thing here is to spot that both of these denominators are quadratics and to think if these can factorise. And actually, yes, they can. So for the denominator of the first fraction, we can rewrite this in a factorised form, because that factorises into x plus 3, x plus 1. On the other side, this one again will factorise into x plus 3, x minus 5. And we're adding the two algebraic fractions together, so I'll just stick a plus sign here. And then what we need, of course, are the numerators, 3 and 7. We need to have a common denominator. Well, x plus 3 is already common in each. Have an x plus 1 over here in this one, but not over here. So to get the x plus 1 common to each denominator, I can multiply the second fraction, both top and bottom, by x plus 1. In a similar way, over here, this fraction, the denominator is mixing x minus 5, which is in this one. So to make it appear in this first fraction, I'm going to multiply both numerator and denominator by the fraction x minus 5. So if we do that, I'm just going to write down our next step. So the first fraction will become 3 lots of x minus 5 as the numerator. For the denominator, I'll do these in terms of what I'm saying is like, what I feel is order of size. I don't know if it's just me being a bit weird, but in my head, plus 1 should come first. Then plus 3. Put the positive numbers first, and then I'll put the x minus 5 last. I don't know why, but that just makes it read better to me. It doesn't really matter, to be honest. I just felt an urge to write it in that order. Then over here, I've got 7 multiplied by x plus 1, which of course I'll just write in now. 7 times x plus 1. And this denominator, again multiplied by x plus 1, will become x plus 1 now, multiplied by what we had before, of course, which is the x plus 3, x minus 5. So now these denominators are common, so we can now combine the two fractions into just a single algebraic single fraction. So I've got x plus 1, x plus 3, x minus 5, and the numerators, this one, 3 times x minus 5 becomes 3x minus 15. Over here, 7 times x gives me 7x, and 7 multiplied by 1, of course, just gives 7. Final step, we can now simplify the numerator, and we're done. So, we're going to have 3x plus 7x, which overall, of course, gives 10x, minus 15 plus 7 overall gives minus 8, and the denominator fully factorised, we can leave as x plus 1, x plus 3, x minus 5. And that's warm-up question 2 complete. Let's now have a look at question 3 on the warm-up. Warm-up question 3, we've got f of x, which is 3x plus 1 over x plus 3 minus 2 all over x squared plus 5x plus 6, where x is any real number, excluding the possibility that x can be minus 2 or minus 3. The reason being, if x were minus 2 or minus 3, this would give a 0 denominator for this last fraction, which of course we cannot compute, it's undefined. We can't divide by 0. So that restriction the function will work. We need to show that this version of f of x simplifies into this version here, which is a single algebraic fraction. So let's just apply what we've learned from 1 and 2 and see if we can somehow get a single common factor here. So I'm just going to begin with what the question says, which is, of course, is f of x. So f of x, I'm going to rewrite the 3x as 3x over 1. This I'm just going to write as it is exactly, so that's 1 over x plus 3. This here, again, the clue is in the question. This will factorise into x plus 2, x plus 3. Whoops, that's a minus, almost forgot. So here, I'm just going to write what we've got here in its factorised form. I'm going to write that as x plus 2, x plus 3. So, once again, we need a common denominator. So, this middle fraction has got x plus 3 in it, but it's missing the x plus 2. So, I'll put the numerator in as well. That was a 2, of course. I could get this middle fraction to have the same denominator as the last if I multiplied the denominator again by x plus 2. But if I do that to the denominator, I need to do the same to the numerator. Over here, this 1 doesn't match at all. So what I could do is I could take this 1 unit and multiply by both these brackets by x plus 2 and by x plus 3. So if we do that next, just take the time to get this nicely set out. So the first fraction will become 3x multiplied by, it's a bit too high, multiplied by x plus 2, x plus 3. And that's all going to be over x plus 2, x plus 3 now. The middle one will become 1 times x plus 2, which of course is just going to be x plus 2. So that's just going to become x plus 2 all over x plus 2 times x plus 3. And the last one, we can just leave as it is for now. So minus 2 all over x plus 2, x plus 3. So now we've achieved our objective of having a common denominator. All these three fractions all have the same denominator, a factorised one, which is x plus 2, x plus 3. So we can now combine the numerators together. So this first one here, if I were to expand x plus 2, x plus 3, of course I'd get this, x squared plus 5x plus 6. So if I take all of these terms and multiply by 3x, we can see hopefully that this first numerator will become x squared times 3x, which will give 3x cubed. The 5x term, 5x times 3x, will give 15x squared. And the constant term 6 multiplied by 3x gives 18x. I've got the plus x plus 2. Then just minus that 2. Extend the fraction. Actually grab hold of it. Oh no, whoa, 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 not that. Hiding something which was meant to be hidden from a previous slide there. So extend that, and then just write it all over x plus 2, x plus 3. So finally, a bit of care, we can simplify this down. So if we do that now, I'm going to have 3x cubed. There's no other cubic terms to simplify with, so that just stays as 3x cubed. 15x squared, again that will just stay as the 15x squared, so I'll leave that as is. The plus 2 and minus 2, I can see clearly those are going to cancel, so may as well do that now. And then 18x plus an extra x, of course, will give 19x. All divided by x plus 2. X plus 3, of course. Which then, we can factorize out an x in the numerator, and we'll have arrived at the result we need. So factorizing out the x, we get x, then brackets 3x squared plus 15x plus 19 all over x plus 2, x plus 3. And finally, we can have a look at worked example 4. At this point, though, just consider the denominators. So for questions 1, question 2, question 3, have a look at consider the single linear factors on the separate fractions. For example, these denominators here, and compare them to the denominator found in the single fraction. You should be seeing now that they actually do repeat, and this is going to be forming the main concept of today's lesson. So to take it one step further and to crystallize this idea, worked example 4, fill in the blanks to these identities below using the expressions written in these boxes. Take care, do mean that. 3 boxes won't be useful. So this could be a trial and error job. I'm going to assume you've had a play around with this, going back and forth and maybe just trying different possibilities, unless you think you've nailed the pattern and know what the easier way of doing it is. But all will be revealed one way or the other. Initially, this first one, what we need to do here is to get a common denominator. I'm not going to do that for you. Assuming you have, what you should have hopefully found is this one becomes 8x plus 31. If you combine that into a single denominator and got the into this and then worked out a single numerator, you should find it's 8x plus 31. So the first one, 8x plus 31 there. This one here, again combining into a single algebraic fraction this time. If you were to get a single denominator and then combine, what you should find, again, these single denominators appear together in the single algebraic fraction. So in any order, for one you need p minus 1 in brackets, and the other you need p plus 1. And finally this one, 2x squared plus 4x plus 9 all over x minus 3 brackets 2x plus 1. Again, look at these denominators. X minus 3 appears over here, and if you've tried it, you should see that 2x plus 1 appears in the other one. I'll shrink that down so it fits into the box as it should, and there we go. So for ones which we've not used, it says 3 boxes won't be useful. So the ones which weren't any use, of course, were 5x plus 18, the x plus 3 we didn't use, nor did we use the p squared minus p. So those there are the boxes which had no use. So part B, just trying to really drive home the main point. What do you notice? What do we notice about the denominators on both sides of each of these 3 identities? So essentially, the factorized algebraic denominators in the single fraction are exactly the same denominators that are separated when that single fraction is written equivalently as multiple single algebraic fractions. So when you take a single fraction and split it into single different algebraic fractions, that's called essentially writing it in partial fractions. So partial fractions, which is the main theme today, is when we're going to take a single fraction, for example this one, and split it into two or more. This is called partial fraction decomposition, where we split one algebraic fraction into two or more. So let's have a look how to do that now we've done the warm-up questions. So partial fractions. Let's explain what we mean by this. So it's absolutely vital in A-level maths that you master algebraic fractions. There's no two ways about it, and just algebraic manipulation generally as an absolute priority. So if you've struggled with any of the warm-ups questions 1 to 3, at this stage of your journey you should have found that fairly, reasonably straightforward. I'm not saying completely painless, but relatively so, especially compared to some of the other stuff you've seen. If that's not the case, you are, and I can't stress this enough, you are very strongly recommended to complete exercise 1B and exercise 1C in your year 13 blue textbook. Exercise 1B and 1C, in my opinion, well, it's more or less a fact, don't say this arrogantly. Exercise 1B and 1C are no more really than a recap of GCSE. And so if you've struggled with questions 1 to question 3, I'm not saying panic, but what I am trying to say in the nicest possible way is just get brushed up as soon as possible with your algebraic manipulation skills. We can't dawdle with such a big course. So if you have struggled with those, try 1B and 1C as a priority before you do the suggested exercises, which I'm going to mention at the end. Assuming though they are more or less okay, let's just go forward and talk about the partial fractions. So the ones we've encountered at GCSE, the algebraic fractions, include problems in which algebraic fractions are added or subtracted. Yes, sometimes as well multiplied or divided, but I'm focusing here on adding and subtracting algebraic fractions. So how we do that is we find a common denominator so that the separate fractions are added or subtracted, merged, if you like, into a single fraction. When that happens, the factorized denominator of the single algebraic fractions is comprised of the two denominators from the separate initial fractions. So essentially, the single factorized denominator is comprised of the single linear denominators in the individual fractions from whence it came. So for example, in warm-up 1A, we saw that adding these two algebraic fractions together with denominators 2p plus 1 and p minus 1, those exact same denominators appear in the single algebraic fraction. So this one plus that one, again, appear here and there. And actually, this will always be the case. Because that will always be the case, we can now generalize this fact to enable us to split up, another word for that is decompose, a single algebraic fraction with a factorized denominator into separate fractions with linear denominators. And again, this can be extended to a fraction with more than two factors. So, for example, the algebraic fraction 5 over x plus 1 x minus 3 would split into a over x plus 1 plus b over x minus 3, where a and b are to be found, whereas, say, a different fraction, 5 over x brackets x plus 1 brackets x plus 3, this one has three separate linear factors, here, here, here. So this one would split into three separate algebraic fractions, with each of these three linear factors found as denominators in the three individual fractions, where in each case a, b, and c are just coefficients, constants to be found. And of course, this a and b won't be the same necessarily, won't be the same a and b as these two over here. There are almost always with maths a variety of different methods for doing anything. So there's a variety of different methods for finding these unknown coefficients. I'm just going to show you two in this next worked example. And of these two, one is my strong favourite. That's just my personal preference. That's how my teaching will lead with this personal preference of mine. But the other one is just as valid. So if I don't mention the other one as much in future videos, it's not because it's not valid, it's just not my personal preference as a teacher. So, worked example 1. Express 3x plus 10 all over x plus 3 brackets x plus 4 as partial fractions by comparing coefficients. This, by the way, is a method I'm not too fond on. substitution, part B, is my much preferred method. So what I'm going to do here, I'm going to show you that the actual starting point is one and the same, whether we compare coefficients or we use substitution. And this method I'm going to show you is slightly different from the textbook. And again, a lot of maths is personal preference, as long as the methods are valid, of course. I'm just splitting here this box into A and B, if you're wondering what I'm doing here. So that'll be A and B. But the initial first step is actually going to be the same, whether I choose A or B as my preferred method. So first off, we're just going to start here by splitting this into partial fractions. Based on what I said earlier, we know that 3x plus 10 all over x plus 3 times x plus 4, we can split this into some number a over the first factor plus some number b over the other factor. Now what I'm going to do is multiply both sides of this by the entirety of all the linear denominators on the first fraction. So I'm going to multiply everything by x plus 3 and by x plus 4. What that'll give us on the other side, this fraction, if I multiply the denominator, that undoes the denominator being there at all, that'll just give us 3x plus 10. Now if I do a divide by x plus 3, multiplied by x plus 3, x plus 4, the x plus 3 will cancel, so I'll just get a lots of x plus 4 plus b lots. In the same way, the x plus 4 will cancel, I'll just get x plus 3. And so what we're using here essentially is this result. So now we've got that, we can now either use part A or part B. But first of all, how does that help us with part A? Well, I'll show you. So I'll just take all that, copy and paste, and again, that's our starting point for both A and B. So part A, comparing coefficients. So if we were to imagine just the either x terms or the constant terms, let's go first of all, I would suggest, for the x coefficients. So let's compare x coefficients. Coefficients, by the way, in case you're not familiar with that word, you should be, but if not, it just means the constant terms in front of the variables. So the coefficient of x is just 3. So I've got 3x over here. On the other side, if I expanded it out, I'd have a lots of x plus b lots of x, which of course I can factorize out an x and say it's a plus b lots of x. So in other words, 3x's must be the same as a plus bx's. So therefore, 3 equals a plus b. If I now to compare the constants, just for numbers if you like, I'll stress again, this isn't my favoured method. Part B I think is easier, but you can draw your own conclusions. So just comparing constants. On the left I've got 10. On the right, if I expanded out, I'd have a times 4, which is 4a, plus b times 3, which of course is 3b. What you should spot now is, essentially, I have two lots of equations. I've got two simultaneous equations. So what I can do is solve these. So if I've got here 3 equals a plus b, if I just multiply the whole thing by 4 on both sides, and then we'll arrive at 12 equals 4a plus 4b. And now I can solve simultaneously. So 4a's are the same. In fact, everything's the same apart from the top equation I've highlighted in green has one extra b, and that's 2 higher. If you want to, you can just do one equation, take away the other. Either way around, you should hopefully see that b is 2. Then knowing b is 2, I can substitute that in to either one of these equations. I'm going to pick, I don't know, let's go for the top one. So 12 equals 4a plus 4 lots of b, which is 8. Subtract 8, divide by 4. Hopefully you'll see fairly clearly that a would have to be 1. So therefore, f of x, no, it's not called f of x, is it? It's just 3x plus 10 all over x plus 3, x plus 4 can be written as a, which we've worked out is 1, all over x plus 3 plus b, which we worked out was 2, all over x plus 4. So that was A, which we worked out, and we worked out B as well. Whoops, wrong colour, I need a different one. Going to go for pink. B we got was 2, hence 2 there. Now, substitution. Essentially, what we do here is we pick different values of x such that one of these brackets, which we don't know, will vanish, so we can focus upon the other. So -3 and -4 would be good numbers to pick. So if I go for, first of all, x being equal to -4, and sub that value in, over here, 3 times -4 is -12, plus 10, well that gives -2. This bracket here, -4 plus 4 will cancel, so I'm just going to get b, -4 plus 3 is -1. So -2 equals -b, so therefore b equals 2. And then if we were to pick x being -3 to knock out this bracket, 3 times -3 is 9, so -9. -9 plus 10 gives exactly 1. Over here, the b bracket will vanish because -3 plus 3 is 0. Over here, -3 plus 4 is just 1. 1 times a is just a. So therefore, we've got it straight away. We can see that 3x plus 10 all over x plus 3, x plus 4. Once again, same conclusion as you'd rightly expect. We get 1 all over x plus 3 plus b, which is 2, all over x plus 4. And I may as well use the same colour coding, why not? And that's worked example 1 complete. Now it's a common misconception to be thinking, oh, so all of these constants we're trying to find will always be whole numbers. Yeah, they might be negative, but they'll always be whole numbers. Well, actually, no. Often, yes, but sometimes not. You may end up with a constant here to be found, which is actually a fraction in itself. That's what worked example 2 now is going to show you. So don't always rely on these being integers. Don't reject or think you're wrong if you end up with a fraction. So let's have a look at worked example 2. So, worked example 2. Express 4x squared minus 8x plus 16 all over x cubed plus 2x squared minus 8x as partial fractions. The first thing here, we need to see if we can sort out this denominator. This isn't factorized, but immediately you should see we can factorize out an x from here. So let's do that first. So x cubed plus 2x squared minus 8x, factorize out the x, that gives us x brackets x squared plus 2x minus 8. So I need two numbers that multiply together to give negative 8 but add to positive 2. Those values are going to be positive 4 and negative 2. So this I can rewrite as x brackets x plus 4 brackets x minus 2. And this form is much simpler because I can now decompose this into its three separate linear factors. So just write this here so we can use it. So therefore, all of this we can rewrite in factorized form on the denominator. So I've got 4x squared minus 8x plus 16 all over x brackets x plus 4 brackets x minus 2, which can now write as three separate fractions. 1, 2, 3, where each denominator of the separate fractions of denominators here which were factorized. So x plus 4, x minus 2. And we need to find the constant terms on the top, a, b, and c. Again, my suggestion here, we're going to multiply everything on both left and right by the entirety of this factorized denominator in the first fraction. So we're going to multiply everything by x brackets x plus 4 brackets x minus 2. What that now gives us is, after multiplying the entirety of the denominator by the first fraction, we'll just have the numerator of it remaining. So over here we have 4x squared and minus 8x plus 16, and on the other side we're going to have a divided by x times x will cancel, so it's going to be left with a multiplied by these two brackets, the x plus 4 and x minus 2. In a similar way with the b term, b over x plus 4 multiplied by x plus 4, the x plus 4 bracket will cancel, leaving us just with b times x minus 2. And then the c bracket, divided by x minus 2 times by x minus 2, those two will cancel. So I'm just going to have c times x multiplied by x plus 4. Now it's a case of picking different values of x systematically to eliminate either a, b, or c, so we can focus on just one of these unknown coefficients. If we have a look at b and c, next to them I've got just an x, so I could substitute x being 0, which would knock out the b stuff and the c stuff immediately, because b times 0 and c times 0 will just mean these two terms vanish. So let's do that first. Let x equal 0. If x equals 0, that becomes nothing, that becomes nothing. The left just becomes 16. On the right, I'm going to get a multiplied by nothing plus 4, which is 4, times nothing minus 2, which is minus 2. As I said, this and the c will vanish. So I just get 16 equals a multiplied by negative 8. So if I divide both sides by negative 8 to find what a is, a has to be negative 2. So I've worked out one of them. I've got a, which is negative 2. Now what we could pick, we could maybe go to eliminate this b bracket over here. If I eliminate, if I were to pick x equals 2, that would eliminate a and b, because if x was 2, that bracket becomes 0, so I get this times 0, which vanishes, and this times 0, which vanishes as well. So let's make that our next choice. Let x equal 2. So if x equals 2, 4 times 2 squared, 4 times 4 is 16, minus 8 times 2 minus 16 is nothing. 16 takes 16 is nothing, plus 16, again weirdly, I still get 16. Over here, the a terms vanish, b terms vanish. I'll just have c times x, which is 2, times x plus 4, which is 2 plus 4, which is 6. So therefore c is going to be 16 divided by 12, which is 4/3. So I've got what c is. C is 4/3. Finally, let's work out what b is. So how can I make the a stuff and the b stuff vanish? Well, a and c have the bracket x plus 4. So I'm going to go for x being minus 4 to make those two brackets vanish and become nothing. Then I can focus in on b. So now, let x be minus 4. If x is negative 4, 4 times minus 4 all squared, well, minus 4 times minus 4 is 16. 16 times 4 is 64. So I'm going to get 64. Minus 8 times minus 4 is positive 32. Then just plus for 16. And then over on the other side, the a bracket will vanish, but I'll have b times x, which means b times minus 4 times minus 4 minus 2, which is minus 6. So if I simplify this, on this side, 64 plus 32 is 96. 96 plus another 16 is 112. So 112 equals minus 24b. If I now divide both sides by negative 24, minus times a minus, my mistake is a positive. How silly. So no, I get 112 equals just 24b, then dividing by 24, I get that b has to be 112 over 24, which simplifies to 14 over 3. I can now piece all that together, and we're going to get our answer. So b is 14 over 3. So therefore, we can write it as our final answer. So 4x squared minus 8x plus 16 all over x cubed plus 2x squared minus 8x. That can be written as minus 2 over x plus b. Now I can either write b as 14 over 3 all over x plus 4, or I can write it like this. I can put it as 14 on the top and then the 3 on the denominator. So 14 over 3 lots of x plus 4, and then c, again I can either put plus 4/3 all divided by x minus 2, or I could put the 4 on the numerator and the 3 on the denominator, which is what I'm actually going to do. So c 4/3 x minus 2. So essentially I can just colour code for you what a, b and c are. A minus 2. The b term was 14 over 3, which is that there, and the c term 4/3, which is that one. And that's our final answer. So we're good. Now it's over to you to get some much needed practice on these skills. So in your blue book, if you turn to page 11 and 12, exercise 1D, and try questions 2 through to question 7, and I would also suggest, if you can remember some algebraic division and the factor theorem, to try the challenge question 2 found after question 7. So keep going strong, keep plugging away, let me know if you're stuck, check your answers regularly as you work through. That's really, really crucial, and never give up. So keep going, and I'll hope to see you all soon. So from me, it's goodbye for now.